Hi, my name is Brian Carlett, and this is Securing the Right to Repair, the intersection of cybersecurity and sustainability. My project is motivated by the growing e-waste stream or electronic waste stream. So all of your electronic devices that you no longer want or become obsolete end up in landfills. And in 2022 alone, there were 62 million tons of e-waste. That's every year, and this number is only increasing. Um, as a solution to addressing e-waste, Right to Repair promises that you can extend the life of your electronics by empowering the consumer to make these repairs and changes. In order to do that, you have to have buy-in from manufacturers and designers who are willing to share their design schematics, as an example. And what you see is that in the legislation coming out over the past decade, um, industry has really fought against this, and this is especially prevalent in the game console industry, which is what I will focus on for the rest of my project. In the game console industry, they are excluded because game console manufacturers claim that sharing their schematics will lead to piracy. Um, so they received an exemption to right to repair. Well, the problem is, in a lot of these game consoles, what actually fails and what's repairable has nothing to do with security. And so what they're trying to lock down, the basis for their argument, is preventing people from making real repairs, which I would say would be 90% of the parts that are in a device are not security relevant. And you can see this by reviewing legislation such as New York's Digital Fair Repair Act and looking at the Digital Millennium Copyright Act in exemption section 1201. So what's to come is I'm going to do a case study on the Nintendo Switch Lite, um, where I've identified some security issues and attack methods that are prevalent today. And I will explore these attack methods and I will use economics as a way to evaluate the solutions. I chose the Switch Lite because of its availability, its price point on secondhand sites, and the fact that there are existing vulnerabilities against this SoC that powers the Nintendo Switch Lite. There are also a lot of open source tools available. There's a massive community of reverse engineers and modders out there that have put together all sorts of information because Nintendo won't put out their schematics or any information to help people repair things. So there, for example, there's a site called usoldering.com. It's a retired technician who literally fly wired to every point on the board and created a file that you can open up in open board view, and it'll show you where each electrical connection is, and that's in the bottom left. As it turns out, the NVIDIA Tegra X1 has an unpatchable vulnerability. And when I say unpatchable, that means that the vulnerability is actually part of the manufacturing process while the chip is being fabricated by NVIDIA. So the second this chip comes off the assembly line, it's vulnerable. And these chips are included in the Nintendo Switch, making every single Nintendo Switch vulnerable to this attack. So what happens is when the chip is powered up, it first executes a boot ROM, and this boot ROM is vulnerable to a fault injection attack. So if you were to implement a perfectly timed glitch, you could manipulate the code execution flow and insert a payload to redirect execution to the micro SD card. And that is exactly what's done on the Nintendo Switch. So this is a blown up version of the OWASP threat model that I created. Uh, in the red box is the mod chip. So what happens is that the crowbar circuit to ground uh, hijacks your data flow essentially and redirects it to the SD loader and to the SD card. So uh, from the micro SD card, you can boot a payload.bin, and from there you go into a custom bootloader called Hecate, and from there the security checks and signature verifications are disabled, and you can boot into any of the ARM compatible operating systems that are out there. So there's an Android and Linux OS. There's a custom OS called Atmosphere that essentially is a copy of Nintendo's um, official Horizon operating system. PicoFly is an open source voltage glitching attack against the Nintendo Switch. So it has been commercialized by Chinese resellers, mainly on AliExpress and Alibaba. So I found that they are using the 100% open source code for the Raspberry Pi 2040 that can be found in the linked GitHub. Um, the hardware cost for these parts I found on DigiKey to be about $4 each, and these kits retail on the Chinese e-commerce websites for about $12 each. Installing the PicoFly mod chip is pretty straightforward if you have microsoldering experience. Essentially, there is a two-layer printed circuit board with some flex cables that get soldered to test points on the Nintendo Switch Lite motherboard. The test points you're seeing in the top left image are the communication lines between the eMMC and the SoC. And in the top right, those are the decoupling capacitors that you solder a crowbar flex cable circuit to the Tegra interposer board, which is in the bottom right. That bottom right is the blown up view of the area that's being attacked. And in the bottom left is the eMMC signals circled in red that are being exploited. So to evaluate PicoFly, I wanted to take an economic approach. I wanted to determine if this was a lucrative market, if PicoFly was profitable for the resellers on AliExpress. So from my hardware bomb, I calculated $3.66 for all the parts. I estimated the assembly and overhead cost of building these boards to be um, twice the hardware bomb, so $7.32. Uh, so from a user perspective, the cost of a PicoFly installation should be adjusted for risk. And I took install time of 2 hours and a labor rate of $40 an hour, $12 for the cost of the boards, and a failure probability of 20%, and a $200 failure cost, so replacing your console. And adjusted for risk, that comes out to $132. So in order to mitigate these mod chips, the failure probability and the install time are what need to be manipulated and increased. Um, and I also wanted to show that the cost impact to Nintendo is significant. If you assume that the average gamer has 5 games and paid $40 each for it, assuming 5% of consoles are modded out of the 152 million sold, that's $304 million in lost revenue since March of 2017 when the console released. So what can you do to defend against these mod chips? So first, PicoFly was so easy to install because Nintendo prioritized design for manufacture instead of hardware security. And what that really means is that uh, they left test points on the board that attackers and consumers could easily probe and even solder to exploit. Um, so I want to propose a few design considerations that can be done up front to prevent mod chip installs for any general kind of design. So when your design is ready to go to production, you should remove any test points from your sensitive traces. This will just make it harder for attackers to access and probe your lines. Um, Fault injection attacks really exploit the reset line. Uh, when an attacker is implementing a fault injection attack, they'll typically loop through different timing points, and they use that reset line to reinitialize a console and automate their testing. So obfuscating that in a mid layer of your printed circuit board will make it much harder to uh, access. You and designers can also explore adding embedded resistors and capacitors for sensitive traces. So taking those resistors and capacitors on the top and bottom side of the board and actually building them into a mid layer on the printed circuit board. And finally, you can implement things like anti-tamper meshes, which when an attacker drills into your board, if the mesh is broken, it can trigger a security change on your SoC. In this slide, I wanted to demonstrate the efficacy of the controls that I am proposing. So I did note the change to the Picofly install time for each control, as well as a change into the failure probability percent for each control. And I did want to put a cost to the manufacturer just to assess the level of effort it would take to implement these changes. And what you see is that today the cost, um, risk adjusted cost to a user to install a Picofly chip is about $132. Um, Implementing the controls, so just reducing your test points, will increase the cost, and ideally you want that to be as high as you can get it, and that will be your disincentive to modify your console and pirate it, because the cost of legally owning these games will be far less than it would be to mod your console. So my proposed solutions and research does have limitations. Ideally, these controls that I'm proposing, the PCB design changes that I'm proposing, need to be evaluated and researched in a long-term study. Ideally, I would create a printed circuit board with the changes and have a skilled technician familiar with the Picofly installation to try these installs on my board with the different security measures. And from there, I can refine my time and cost approach. Um, I also tried to consult the Institute of Printed Circuits IPC specifications that outlines industry guidelines for implementing things like embedded passive resistors and capacitors, and quality and trusted electronics design, manufacture, and assembly processes. But of course, they're hidden behind a paywall and they want you to pay for it. For future work, I want to extend the testing and research on voltage fault injection to other industries that use the NVIDIA Tegra chips. For example, the NVIDIA Jetson dev kits are widely available, so testing volt injection on those may be beneficial. There are many devices out there that use the Tegra chipsets. The X2 is the one of the most recent ones. Um, so that includes the Tesla vehicles, the Mercedes-Benz infotainment systems. There are some edge computing devices out there, and then most recently, the Nintendo Switch 2 was announced to be using a variant of the Tegra X2. So, in conclusion, Picofly is a commercialized and open source voltage fault injection attack that has been proliferated through AliExpress sellers, so mostly Chinese-based uh, sellers, and it's impacted Nintendo to the level of $300 million, in the assumption that 5% of all consoles that they've sold have a Picofly chip in them. Um, for future designs, Nintendo and other designers should obfuscate their test points and um, think about things such as anti-tamper meshes and obfuscating reset lines to prevent against mod chips that do volt injection attacks. Uh, I also believe that what I've demonstrated is that there is a basis for uh, designers to be concerned about sharing schematics and information for security relevant parts. However, that's only a small subset of the chips that are on that board. Everything that I didn't cover honestly should be included in right to repair legislation. And I hope this helps provide legislators and companies uh, reason to consider including themselves on that legislation and being a leader in that area. Thanks for listening to my presentation, and I hope you enjoyed it.